Hello. We wrapped up our lecture on the Laplace equation last time. So from today, I'm gonna begin the discussion on the Poisson equation and how to solve such an equation. So first of all, the Poisson equation is an equation which take into account the presence of charge. So the right hand side is no longer zero, and which that obviously complicates the solution. Um, so rather than tackling this as a general problem, we might want to just consider a very special and a very simplified case of the Poisson equation at play. And the case that I have in mind, and I want to consider spending a lot of time on today, is the case of a single charge sitting at a distance of z0 from an infinite conducting plate, which itself is grounded at the zero potential. Okay, and then what we want is to find out the potential distribution in the entire upper half plane, which is equivalent to saying that I want to solve this Poisson equation, assuming the charge density function that's like this. There's a delta function with a center located at the location of the charge. And obviously later we will try to impose the boundary condition that the potential be zero in the entire plane where z coordinate happens to be zero. So that's the kind of problem that we want to solve. And obviously, if you just try to solve this problem by separation of variables or whatever, it sounds pretty daunting. And and here we're not going to do it by that formal method, separation of variables, summing over an infinite series, and so on. But rather, we're going to just solve this problem by a trick. And the trick is called the method of images. And when it works very well. When it doesn't work, we can just say goodbye to such a technique and try to look for other ways of solving the problem. But this problem we're looking at is the problem where the image method works fantastically well, and so I'm gonna introduce you to the technique. So instead of considering this problem of one charge and one infinitely large plate, we're going to consider a problem of one charge and another charge of opposite sign and no plate, no conducting plate in between. Okay, so this is a simple problem of a dipole. Positive q sits here, negative q sits here, and the coordinate of the positive charge is at positive z0, and the coordinate of this guy is at negative z0. So overall, the potential of this dipolar system is simply given by this. Now, quite obviously, the potential uh, that this dipole generates when z is equal to 0. So you have to take z to be 0 here and here. Well, in that case, this difference vanishes. In other words, in the entire plane where z is equal to 0, you just have created a zero potential everywhere. Now, that just happens to be exactly the same requirement as the original problem that we wanted to consider here. Uh, the boundary condition for this problem was that the potential be uniformly equal to zero on this z equal to zero plane. And by coincidence, that condition happens to be exactly satisfied by the potential due to a dipole. Okay, I guess that's strike number one. The strike number two is that if you take the Laplacian of this potential, and since this is nothing but a Coulomb potential, when you take the Laplacian of a Coulomb potential 1 over r, you just end up creating a delta function. And so by that rule, we will just end up with this delta function. Now, there's also a delta function coming from here, the second term, but that delta function will be centered at r equal to minus z0. However, if you just confine your attention to the region above the plate where the coordinates are z greater than 0, then the delta function coming from this second term will be strictly 0. So therefore, in this upper half plane or upper half space, then the result of taking the Laplacian of the potential function is exactly that. But this is nothing but what we had in this original problem. Just insert this charge density function back into the Poisson equation. And what we get is exactly this. So to summarize the situation, we have this simple solution coming from the dipole, and this solution happens to have the correct boundary condition, and it also happens to satisfy the correct Poisson equation. And now, if a solution that you happen to come across should satisfy the correct Poisson equation and also the correct boundary condition, then there's a theorem in electrostatics saying that whatever solution you happen to have come across, as long as they satisfy those two requirements, then that must be the unique and correct solution of the problem. So in other words, at least in the upper half space, this potential must be the exact potential function that we are looking for this problem. Okay. And we got the answer to this problem by a really cheap method. Just consider the alternative problem of a dipole. But it doesn't matter whether we lied or whether we use a trick, a dirty trick or a clever trick or whatever. As long as the solution that we stumble upon happens to be the correct solution, then it is the correct solution. All right, so then with this potential now at the ready, we can, for example, try to calculate the electrostatic field by taking the gradient of this thing and find this expression, for example, minus that expression. Well, this is nothing but the electric field of a point charge at z0 and point charge at minus z0. And there's a different sign here because the charges are opposite. Now, if you take this to the limit of z equal to 0, then you quickly find that these only the z component survives. And this is the magnitude of the z component of the electric field. So that means electric field is all pointing perpendicular to the plate. And of course, this is completely natural because this plate is supposed to be a conducting one, equipotential. So there's no tangential component of the electric field allowed, and the only component possible is the normal one. And in this problem, the normal direction is the z. Okay, so this is the electric field that that's pointing upward in the z greater than 0 region. And if you recall what you learned from applications of Gauss theorem a long time ago, then actually the strength of the electric field on the surface is telling us exactly how much charge density is sitting on top of that conducting surface. So by application of the Gauss theorem, we can deduce that the surface charge density divided by the dielectric constant must be that electric field along the z direction. Okay. So I initially wrote down a factor 2 in the denominator, but quickly erased it because a factor 2 would imply that there's electric field emanating in both positive z and minus z direction. However, in this problem, there's no electric field in the negative z region because of the screening. So the only electric field available is on one side of the plate where there's a point charge. Okay, so by relating these charge density to the electric field, we come up with this function form for the charge density on the plate. So what happens is that you introduce a positive charge somewhere near the plate, and then by electrostatic attraction, some negative charges start to accumulate on this conducting plate. And obviously, the closer you are to the charge, there's more of the negative charge being induced. Okay, and as you move further and further out, then the amount of induced charge will also decrease. All right, so where were we? Yeah, so you can see that right underneath the positive charge, rho would be 0, and you have the most amount of induced charge. Then as you move further and further out, the induced charge somehow falls off roughly as the cube, rho to the third power, as you move out from the center. Now, another very interesting fact is that if you integrate this induced charge density over the entire surface of the conductor, then by going through this series of calculations, you can show that the total amount of induced charge is exactly minus q. That is, the induced charge is exactly equal and opposite to the charge that you placed in order to induce the charges on the conducting plates. Okay. So what that means is that if you put a 1 coulomb of charge, point charge, near the metallic surface, then there is equal and opposite amount of charge that's created on I shouldn't say created, that's induced on the metallic surface in order to sort of cancel out the effect of this external charge. Okay, so that's pretty cool. Um, so here's the ultimate electrostatic profile for this problem. Uh, there will be an electric field coming out of this point charge, but we also know that right on the surface of the conductor, the electric field direction has to be perpendicular like this. So somehow this electric field line has to bend over and hit the surface at the right angle. And what happens on the other side of the plate is that there is absolutely no electric field whatsoever. And this is a fantastic manifestation of what we previously called the Faraday cage. Even if you have a strong localized charge on the other side, on one side of the metallic conductor, as long as you happen to be on the other side of it, then you're not going to be able to feel any electric field, and therefore will not even be aware of the presence of this external charge on the other side of the metallic sheet. Okay. And what it says is that the ability to screen out the electric field of an external charge is really a perfect one for a metallic, for a conducting surface. Okay, and the other aspect of this problem that I want to look into is the fact that there must be some attractive force between these plate and the charge. And that's quite obvious because this plate is now negatively charged thanks to the positive charge that you placed nearby. And between a pair of objects that are oppositely charged, there should be some electrostatic attraction. Okay, so I want to be able to calculate exactly how much force is acting on the conducting plane by the external charge. And the amount of force is calculated through integral of this infinitesimal force, which is the electric field multiplied by the infinitesimal charge on the conducting plane. And as I said earlier, this electric field along the z is directly proportional to the charge density. And the infinitesimal charge is also proportional to the charge density multiplied by the area element. So we end up having two factors of the charge density. So the thing to integrate over is this charge density squared multiplied by some geometrical factor. So if you go through all the necessary computations, then I arrive at this this answer. And it turns out that that the answer I got here happens to be wrong by a factor 2. So what that means is that the correct answer is only half of what I got over here. So I must have made a mistake somewhere while going from here down to the very last expression. Okay, so here is the homework problem that I'm giving out to you. I intentionally made a mistake in my calculation and got an answer that's a factor 2, too large. And I want you to find out where I have made that mistake and do the correct calculation and show that indeed the correct answer follows from your correct reasoning. Okay, so that's the challenge that I'm giving out to you. So be sure to include your answer along with the summary of the lecture. Okay, so without further ado, I'm just going to give out the correct answer, and the correct answer is this. Okay, so this is the amount of force that's exerted on the conducting plate by the external charge. And by the law of action and reaction, that's also got to be the force on the charge exerted by the plate. But then you quickly realize that this is nothing but the force that this image charge will exert on the original charge. If you went back to this alternative situation of having a charged dipole with a separation of twice z0. So what that means is that even the force acting on the external charge can be obtained by resorting to this alternative problem of a dipole, where you can immediately write down the answer for the force acting on the charge q. That's just a simple Coulomb's law, and that happens to be the correct answer after all. And that's pretty amazing that you can find all of these answers without really having to go through all the complicated integrals that I just did. Okay, so as a mundane application of this problem that we just solved, now consider the problem of a charge that happens to fly by on top of the metallic surface. So this shaded thing is some kind of flat aluminum sheet, for example. And let's say you happen to have some free electron that happens to fly by. And you might have thought that this electron will continue to move along a straight line. But actually, that's not the case. As soon as you put a charge nearby a metallic plate, there is this phenomenon of induced charge or image charge, and this image charge will attract the physical charge, and therefore the trajectory of the physical particle will be bent towards the metallic plate. So it ends up trapping these what used to be a free charge to the surface of a metal, and not allow that charge to leave the surface. Okay, so this is partly what this is partly what gives rise to the so-called work function, that you need to exert a finite amount of energy to let go of a conducting electron from the surface of a metal. That's because of this image charge effect, image force created by the induced charges. Okay, thank you.